Okay, here we are in the final chapter, chapter 20. Final project: build a multi-thread web server. It's been a long journey, but we've reached the end of the book. In this chapter, we'll build one more project together to demonstrate some of the concepts we've covered in the final chapters, as well as recap some earlier lessons. For our final project, we'll make a web server that says hello and looks like figure 20-1 in a web browser. Figure 20-1, our final shared project. Here is the plan to build the web server. 1. Learn a bit about TCP and HTTP. 2. Listen for TCP connections on a socket. 3. Parse a small number of HTTP requests. 4. Create a proper HTTP response. And 5. Improve the throughput of our server with a thread pool. But before we get started, we should mention one detail. The method we use won't be the best way to build a web server with Rust. A number of production-ready crates are available in crates.io that provide more complete web server and thread pool implementations than we build. However, our intention in this chapter is to help you learn, not to take the easy route, because Rust is a systems programming language. We can choose the level of abstraction we want to work with and can go to a lower level than is possible or practical in other languages. We'll write the basic HTTP server and thread pool manually so you can learn the general ideas and techniques behind the crates you might use in the future. Building a single thread web server. We'll start by getting a single thread web server working. Before we begin, let's look at a quick overview of the protocols involved in building web servers. The details of these protocols are beyond the scope of this book, but a brief overview will give you the information you need. The two main protocols involved in web servers are the Hypertext Transfer Protocol, HTTP, and the Transmission Control Protocol, TCP. Both protocols are request-response protocols, meaning a client initiates a request and a server listens to the request and provides a response to the client. The contents of those requests and responses are defined by the protocols. TCP is the lower level protocol that describes the details of how information gets from one server to another, but doesn't specify what that information is. HTTP builds on top of TCP by defining the contents of the requests and responses. It's technically possible to use HTTP with other protocols, but in the vast majority of cases, HTTP sends its data over TCP. We'll work with the raw bytes of TCP and HTTP requests and response. Listening to the TCP connection. Our web server needs to listen to a TCP connection, so that's the first part we'll work on. The standard library offers a standard net module that lets you do this. Let's make a project in the usual fashion. Now enter the code in listing 20-1, source/main.rs to start. This code will listen to the address 127.0.0.1:7878 for incoming TCP streams. When it gets an incoming stream, it will print connection established. Listing 20-1, listening for incoming streams and printing a message when we receive a stream. Using TCP Listener, we can listen for TCP connections at the address 127.0.0.1:7878 in the address. The section before the colon is the IP address representing your computer. This is the same on every computer and doesn't represent the author's computer specifically. And 7878 is the port. We've chosen this port for two reasons. HTTP is normally accepted on this port, and 7878 is Rust typed on a telephone. Okay. The blind function in this scenario works like the new function in that it will return a TCP listener instance. The reason the function is called bind, is that in networking, connecting to a port to listen to is known as a binding to a port. The bind function returns a result TE, which indicates that binding might fail. For example, connecting to port 80 requires administrator privileges. Non-administrators can listen only on parts higher than 1024. So if we tried to connect to port 80 without being an administrator, binding wouldn't work. As another example, binding wouldn't work if we ran two instances of our program and so had two programs listening to the same port. Because we're writing a basic web server just for learning purposes, we don't worry about handling these kinds of errors. Instead, we use unwrap to stop the program if errors happen. The incoming method on TCP Listener returns an integrator that gives us a sequence of streams. More specifically, streams that type of the type TCP stream. A single stream represents an open connection between the client and the server. A connection is the name for the full request and response process in which a client connects to a server. The server generates a response and the server closes the connection. As such, TCP stream will read from itself to see what the client sent and then allow us to write a response to the stream. Overall, for loop will process each connection in turn and produce a series of streams for us to handle. For now, our handling of stream consists of calling unwrap to terminate our program if the stream has any errors. If there aren't any errors, the program prints a message. We'll add more functionality to the success case in the next listing. The reasons we might receive errors from the incoming method when a client connects to the server is that we're not actually iterating we're not actually iterating over connections. Instead, we're iterating over connection attempts. The connection might not be successful for a number of reasons. Many of them operating system specific. For example, many operating systems have a limit to the number of simultaneous open connections they can support. New connection attempts beyond the number will produce an error until some of the open connections are closed. Let's try running this code. Invoke cargo run in the terminal and then load 127.0.0.1 7878 in a web browser. The browser should show an error message like connection reset because the server isn't currently sending back any data. But when you look at the terminal, you should see several messages that were printed when the browser connection connected to the server. Sometimes you'll see multiple messages print for one browser request. The reason might be that the browser is making a request for the page as well as a request for other resources like favicon.ico icon that appears in the browser tab. It could also be that the browser is trying to connect to the server multiple times because the server isn't responding with any data. When stream goes out of scope and is dropped at the end of the loop, the connection is closed as part of the drop implementation. Browsers sometimes deal with closed connections by re-entering because the problem might be temporary. The important factor is that we've successfully gotten a handle to a TCP connection. Remember to stop the program by pressing Control C when you're done running a particular version of the code. Then restart Cargo Run after you've made each set of code changes to make sure you're running the newest code. Reading the request. It's important the functionality to read the request from the browser. Let's implement the functionality to read the request from the browser. To separate the concerns of first getting a connection and then taking some action with the connection, we'll start with a new function for processing connections. Let's see, in this new handle underscore connection function, we'll read data from the TCP stream and print it so we can see the data being sent from the browser. Change the code to look like this. Look like listing 20-2. Listing 20-2 reading from the TCP stream and printing the data. We bring standard I and out prelude into scope and get access to certain traits that let us read from the right to the stream. In the for loop in the main function, instead of printing a message that says we made a connection, now we call the new handle underscore connection function and pass the stream to it. In the handle underscore connection function, we've made the stream parameter mutable. The reason is that the TCP stream instance keeps track of what data it returns to us internally. It might read more data than we're asking for and save that data for the next time we ask for the data. It therefore needs to be mute because its internal state might change. Usually we think of reading not as not needing mutation, but in this case we need the mute keyword. Next we need to actually read from the stream. We do this in two steps. First we declare a buffer on the stack to hold the data that is read in. We've made the buffer 512 bytes in size, which is big enough to hold the data of a basic request and significant for our purpose in this chapter. If we want to handle requests of an arbitrary size, buffer management would need to be more complicated. We'll keep it simple for now. we pass the buffer to stream.read, which will read bytes from the TCP stream and put them in the buffer. Second, we convert the bytes in the buffer to a string and then print that string. The string from underscore UTF-8 underscore Lucy function takes a reference close bracket U8 close bracket and produces a string from it. The Lucy part of the name indicates the behavior of this function. When it sees an invalid UTF-8 sequence, it will replace the invalid sequence with some kind of character. Looks like a diamond and a question mark. The U plus FFD replacement character. Okay. You might see replacement characters for characters in the buffer that aren't filled by request data. Let's try this code. Start the program and make a request in a web browser again. Note that we'll still get an error page in the browser, but our program's output in the terminal will now look similar to this. Depending on your browser, you might get slightly different output. Now that we're printing the request data, we can see why we get multiple connections from the browser request by looking at the path after request:get. If the repeated connections are all requesting /, we know the browser is trying to fetch / repeatedly because it's not getting any response from our program. Let's break down this request data to understand what the browser is asking of our program. A closer look at HTTP requests. HTTP is a text-based protocol, and a request takes this format. The first line is the request line that holds information about what the client is requesting. The first part of the request line indicates the method being used, such as get or post, which describes how the client is making the request. Our client uses a get request. The next part of the request line is /, which indicates the Uniform Resource Identifier, URI, the client is requesting. The URI is almost, but not quite, the same as a Uniform Resource Locator, URL. The difference between URLs and URIs and URLs isn't important for our purpose in this chapter, but the HTTP spec uses the term URI, so we can just mentally substitute URL for UI here. The last part is the HTTP version the client uses. And then the request line ends in the CRLF sequence. CRLF stands for carriage return and line feed, which are terms from the typewriter days. The CRLF sequence can also be written as \r\n, where \r is a carriage return and \n is a line feed. The CRLF sequence separates the request line from the rest of the request data. Note that when the CRLF is printed, we'll see a new line start rather than \r\n. Looking at the request line data we received from running our program so far, we see that get is the method / is the request URI, and HTTP /1.1 is the version. After the request line, the remaining lines start from the host colon onward are headers. Get requests have no body. Try making a request from a different browser or asking a different address such as 127.0.0.1:7878 test to see how the request data changes. Now that we know that the browser is what the browser is asking for, let's send back some data. Writing a response. Now we'll implement sending data in response to a client request. Responses have the following format. The first line is a status line that contains the HTTP version used in the response. A numeric status code that summarizes the result of the request and the reason phase that provides a text description of the status code. After the CRLF sequence are any headers, another CRLF sequence, and the body of the response. Here's an example response that uses HTTP version 1.1 and has a status code of 200. An OK reason, phase, no headers, and no body. The status code 200 is the standard success response. The text is a tiny successful HTTP response. Let's write this to the stream as our response to successful request from the handle_connection function. Remove the print line exclamation mark that was printed in the request data and replace it with the code in listing 20-3. Listing 20-3, writing a tiny successful HTTP response to the stream. The first new line defines the response variable that holds the success message's data. Then we call as_bytes on our response to convert the string data to bytes. The write method on stream takes and reference close bracket u or square bracket. You know what? I'm going to double check that. That is an open bracket and then a close bracket. Okay. A reference open bracket u a close bracket and sends those bytes directly down the connection. Because the write operation could fail, we use the unwrap on any error results as before. Again, in a real application, you would add error handling here. Finally, flush will wait and prevent the program from continuing until all the bytes are written to the connection. TCP stream contains an internal buffer to minimize calls to the underlying operating system. With these changes, let's run our code and make a request. We're no longer printing any data to the terminal, so we won't see any output other than the output from cargo. When you load 127.0.0.1:7878 in a web browser, you should get a blank page instead of an error. You've just hand-coded an HTTP request and response. Returning real HTML. It's important that the functionality for returning more than a blank page. Let's implement the functionality for returning more than a blank page. Create a new file, hello.html, in the root of your project directory, not in the source directory. You can input any HTML you want. Listing 20-4 shows one possibility. Listing 20-4, a simple HTML file to return in a response. This is a minimal HTML5 document with a heading and some text. To return this from the server when a request is received, we'll modify handle underscore connection as shown in listing 20-5 to read the HTML file and it to the response as body and send it. Okay, listing 20-5, sending the contents of hello.html as the body of the response. We've added a line at the top to bring the standard libraries file system module into scope. The code for reading the contents of a file to a string should look familiar. We've used it in Chapter 12 when we read the conditions of a file for our first in-out project in listing 12-4. Next, we'll use the format exclamation mark to add the file's contents as the body of the success response. Run this code with cargo run and load 127.0.0.1:7878 in your browser. You should see your HTML rendered. Rendered, okay. Currently, we're ignoring the request data in buffer and just sending back contents of the HTML file unconditionally. That means if you try requesting 127.0.0.1:7878 /something-else in your browser, you'll still get back the same HTML response. Our server is very limited and is not what most web servers do. We want to customize our response depending on the request and only send back the HTML file for a well-formed request /. Validating the request and selectively responding. Validating the request and selectively responding. Right now our web server will return the HTML in the file no matter what the client requests. Let's add functionality to check that the browser is requesting / before returning the HTML file and return an error if the browser requests anything else. For this, we need to modify handle underscore connection as shown in listing 20-6. This code checks the content of the request received against what we know a request for / looks like and adds if and else blocks to treat requests differently. Listing 20-6, matching the request and handling requests to / differently from other requests. First, we hardcode the data corresponding to the / request to the get variable. Because we're reading raw bytes into the buffer, we transform get into a byte string by adding the B .. byte string syntax at the start of the content data. Then we check whether buffer starts with the bytes in get. If it does, it means we've received a well-formed request to /, which is the success case we'll handle in the if block that returns the contents of our HTML file. If buffer does not start with the bytes in get, it means we've received some other request. We'll add code to the else block in a moment to respond to all other requests. Run this code now and request 127.0.0.1:7878. You should get an HTML in hello.html. If you make any other requests such as 127.0.0.1:7878 / something dash else, you'll get a connection error like those saw when requesting the code in listing 20-1 and listing 20-2. Now let's add the code in listing 20-7 to the else block and return a response with the status code 404, which signals that the content for the request was not found. We'll also return some HTML for a page to render in the browser indicating the response to the end user. Listing 20-7, responding with status code 404 and an error page if anything other than / was requested. Here our response has a status line with status code 404 and the reason phrase not found. We're still not returning headers, and the body for the response will be the HTML in the file 404 HTML. You'll need to create a 404 HTML file next to hello.html for the error page. Again, feel free to use any HTML you want to use. In this, use the example HTML in listing 20-8. Listing 20-8, simple context for the page to send back with any 404 response. With these changes, run your server again, requesting 127.0.0.1:7878 should return the contents of hello.html, and any other requests like 127.0.0.1:7878 / foo should return the error HTML from the 404 HTML. Should return the error HTML from 404 HTML. Okay, a touch of refactoring. At the moment, the if and else blocks have a lot of repetition. They're both reading files and writing the contents of the file to the stream. The only differences are the status line and the file name. Let's make the code more concise by pulling out these differences into separate if and else lines that will assign the value of the status line and the file to variables. We can then use those variables unconditionally in the code to read the file and write the response. Listing 20-9 shows the resulting code after replacing a large if and else blocks. Listing 20-9, refactoring the if and else blocks to contain only the code that differs between the two cases. Now, the if and else blocks only return the appropriate values for the status line and file name in a tuple. We then use deconstructuring to assign these two values to status underscore line and file name using a pattern in the let statement, as discussed in Chapter 18. The previously duplicated code is now outside the if and else block and uses the status underscore line and file name variables. This makes it easier to see the difference between the two cases, and it means that we have only one place to update the code if we want to change how the file reading a response writing work. The behavior of the code in listing 20-9 will be the same as the listing in 20-8. Awesome. We now have a simple web server in approximately 40 lines of Rust code that responds to one request with a page of content and response to all other requests with a 404 response. Currently, our server runs in a single thread, meaning it can only serve one request at a time. Let's examine how that can be a problem by simulating some slow requests. Then we'll fix it so our server can handle multiple requests at once. Turning our single-threaded server into a multi-threaded server. Right now, the server will process each request in turn, meaning it won't process a second connection until the first is finished processing. If the server received more and more requests, this serial execution would be less and less optimal. If the server receives a request that takes a long time to process, subsequent requests will have to wait until the long request is finished. Even if new requests can be processed quickly, we'll need to fix this, but first we'll look at the problem in action. Simulating a slow request in the current server implementation. We'll look at how a slow processing request can affect other requests made to our current server implementation. Listing 20-10 implements handling a request to /sleep with a simulated slow response that will cause the server to sleep for 5 seconds before responding. Listing 20-10 simulating a slow response by recognizing /sleep and sleeping for 5 seconds. This code is a bit messy, but it's good enough for simulation purposes. We created a second request, sleep, whose data our server recognizes. We added the else if after if block to check for the request to /sleep. When the request is received, the server will sleep for 5 seconds before rendering the successful HTML page. You can see how primitive our server is. Real libraries would handle this recognition of multiple requests in a much less verbose way. Start the server using cargo run. Then open two browser windows, one for http://127.0.0.1:7878/ and the other for http://127.0.0.7:7878/ If you enter the /URL a few times, as before, you'll see it respond quickly. But if you enter /sleep and then load /, you'll see that / waits until sleep has slept for its full 5 seconds before loading. There are multiple ways we could change how our web server works to avoid having more requests back up behind a slow request. The one we'll implement is a thread pool. Improving throughput with a thread pool. A thread pool is a group of spawn threads that are waiting and ready to handle a task. When a program receives a new task, it assigns one of the threads in the pool to the task, and the thread will process the task. The remaining threads in the pool are available to handle any other tasks that come in while the first thread is processing. When the first thread is done processing its task, it's returned to the pool of idle threads ready to handle a new task. A thread pool allows you to process connections concurrently, increasing increasing the throughput of your server. We'll limit the number of threads in the pool to a small number to protect us from denial of service (DOS) attacks. If we had our program create a new thread for each request as it came in, someone making 10 million requests to our server could create havoc by using up all of our server's resources and grinding the processing to results to a halt. Rather than spawning unlimited threads, we'll have a mixed number of threads waiting in the pool. As requests come in, they'll be sent to the pool for processing. The pool will maintain a queue of incoming requests. Each of the threads in the pool will pop off a request from this queue, handle the request, and then ask the queue for another request. With this design, we can process n requests concurrently, where n is the number of threads. Each thread is responding to a long-running request. Subsequent requests can still back up in the query, but we've increased the number of long-running requests we can handle before reaching that point. This technique is just one of the many ways to improve the throughput of a web server. Other options you might explore are in the fork/join model and the single-threaded async in-out model. If you're interested in this topic, you can read more about other solutions and try to implement them in Rust. With a low-level language like Rust, all of these options are possible. Before we begin implementing a thread pool, let's talk about what using a pool should look like. When you're trying a design code, writing the client interface first can help guide your design. Write the API of the code so it's structured in the way you want to call it. Then implement the functionality within the structure rather than implementing the functionality and then designing the public API. Similar to how we use test-driven development in the project in Chapter 12, we'll use compiler-driven development here. We'll write the code that calls the function we want, and then we'll look at errors from the compiler to determine what we should change next to get the code to work. Code structure: if we could spawn a thread for each request. First, let's explore how our code might look if we did create a new thread for every connection. As mentioned earlier, this isn't our final plan due to the problems with potentially spawning an unlimited number of threads, but it is a starting point. Listing 20-11 shows the changes to make main to spawn a new thread to handle each stream within the for loop. Listing 20-11, spawning a new thread for each stream. As you learned in Chapter 16, thread : spawn will create a new thread and then run the code in the closure in the new thread. If you run this code and load /sleep in your browser, then / in two more browser tabs, you'll indeed see that the requests to / don't have to wait for the /sleep to finish. But as we mentioned, this will eventually overwhelm the system because you'd be making new threads without any limit. Creating a similar interface for a finite number of threads. We want our thread pool to work in a similar, familiar way to switching from threads to a thread pool doesn't require large changes to the code that uses our API. Listing 20-12 shows the hypothetical interface for the thread pool struct that we want to use instead of thread : spawn. Listing 20-12 our ideal thread pool interface. We use thread pool : new to create a new thread pool with the configurable number of threads. In this case, 4, then in the for loop pool.execute has a similar interface as thread : spawn in that it takes a closure the pool should run for each stream. We need to implement pool.execute so it takes the closure and gives it to a thread in the pool to run. This code won't yet compile, but we'll try so that the compiler can guide us in how to fix it. Building the thread pool struct using compiler-driven development. Make the changes in listing 20-12 to source/main.rs and then use the compiler errors from cargo check to drive our development. Here is the first error we get. Great, this error tells us we need a thread pool type or module, so we'll build one now. Our thread pool implementation will be independent of the kind of work our web server is doing, so let's switch the hello crate from the binary crate to a library crate to hold our thread pool implementation. After we change to a library crate, we could also use a separate thread pool library for any work we want to do using a thread pool, not just for server web requests. Create a source/library.rs that contains the following, which is the simplest definition of a thread pool struct that we can have for now. Then create a new directory, source/bin, and move the binary crate rooted in source/main.rs into source/bin/main.rs. Doing so will make the library crate the primary crate in the hello directory. We can still run the binary in source/bin/main.rs using cargo run. After moving the main.rs file, edit it to bring the library crate in and bring thread pool into scope by adding the following code to the top of source/bin/main.rs. This code still won't work, but let's check it again to get the correct error that we need to address. This error indicates that next we need to create an associated function named new for thread pool. We also know that new needs to have a parameter that can accept 4 as an argument and should return a thread pool instance. Let's implement the simplest new function that will have those characteristics. We chose unsize as the type for the size parameter because we know that a negative number of threads doesn't make any sense. So let's see, also we know that use this for as the number of elements in the collection of threads is, let's see, which is the unsized type is for. Which is what the unsized type is for, as discussed in the integer types section of chapter 3. Let's check the code again. Now we get a warning and an error. Ignoring the warning for a moment, the error occurs because we don't have an execute method on thread pool. Recall from the creating a similar interface for infinite number of threads section that we decided our thread pool should have an interface similar to thread : spawn. In addition, we'll implement the execute function so it takes the closure it's given and gives it to an idle thread in the pool to run. We'll define the execute method on thread pool to take a closure as a perimeter. Recall from storing closures using generic perimeters and the function traits section in chapter 13 that we can take closures as perimeters with three different traits: function, function mute, and function once. We need to decide which kind of closure to use. We know we'll end up doing something similar to the standard library thread : spawn implementation. So we can look at what bounds the signature of thread : spawn has on its perimeter. The documentation shows us the following. The F-type perimeter is the one we're concerned with here. The T-type perimeter is related to the return value, and we're not concerned with that. We can see that spawn uses function once as the trait bond on F. This is probably what we want as well, because we eventually pass the argument we get to execute to spawn. We can be further confident that function once is the trait we want to use, because the thread for running the request will only execute the request closure one time, which matches the once in function once. The F-type perimeter also has a trait bound send and a lifetime bound static, which are useful in situations. We need to send the transfer the closure from one thread to another, and that's single quote static, because we don't know how long the thread will take to execute. Let's create an execute method on thread pool that will take a generic perimeter of F with these bounds. We still use the parentheses after function once, because this function once represents a closure that takes no perimeters and returns the unit type parentheses. Just like function definitions, the return type can be omitted from the signature. But even if we have no perimeters, we still need the parentheses. Again, this is the simplest implementation of the execute method. It does nothing, but we're trying only to make our code compile. Let's check it again. We're receiving only warnings now, which means it compiles. But note that if you try cargo run and make a request in the browser, you'll see errors in the browser that we saw at the beginning of the chapter. Our library isn't actually calling the closure passed to execute yet. Note, a saying you might hear about languages with struct compilers, such as Haskell and Rust, is if the code compiles, it works. But this saying is not universally true. Our project compiles, but it does absolutely nothing. If we were to build a real complete project, this would be a good time to start writing unit tests to check that the code compiles and has the behavior we want. Validating the number of threads in new. We'll continue to get warnings because we aren't doing anything with the parameters to new and execute. Let's implement the bodies of these functions with the behavior we want. To start, let's think about new. Earlier, we chose an unsigned type for size perimeter, because a pool with a negative number of threads makes no sense. However, a pool with 0 threads also makes no sense, yet 0 is a perfectly valid usize. We'll add a code to check that size is greater than 0 before we return a thread pool instance, and have the program panic if it receives 0 by the assert exclamation mark macro, as shown in listing 20-13. Listing 20-13, implementing thread pool : new to panic if size is 0. We've added some documentation to our thread pool with doc comments. Note that we followed good documentation practices by adding a section that calls out the situation which our function can panic, as discussed in Chapter 14. Try running cargo doc -- open and clicking the thread pool struct to see what the generated docs for new look like. Instead of adding the assert exclamation mark macro as we've done here, we could make new return a result like we did with configure : new in the in-out project in listing 12-9. But we've decided in this case that we're trying to create a thread pool without any threads should be an unrecoverable error. If you're feeling ambitious, try to write a version of new with the following signature to compare both versions. Creating space to store the threads. Now that we have a way to know we have a valid number of threads to store in the pool, we can create those threads and store them in the thread pool struct before returning it. But how do we store a thread? Let's take another look at the thread : spawn signature. The spawn function returns a join handle T, where T is the type that the closure returns. Let's try using join handle 2 and see what happens. In our case, the closures we're passing to the thread pool will handle the connection and not return anything, so T will be the unit type parentheses. In code, the code in listing 2014 will compile, but doesn't create any threads yet. We've changed the definition of thread pool to hold a vector of thread : join handle less than parentheses greater than instance. Initialize the vector with a capacity of size. Set up a for loop that will run some code to create the threads and return a thread pool instance containing them. Listing 20-14, creating a vector for thread pool that holds the threads. We've brought standard : thread into scope in the library crate because we're using thread : join handle as the type of the items in the vector in thread pool. Once a valid size is received, our thread pool creates a new vector that can hold size items. We haven't used the width _ capacity function in this book yet, which performs the same task as vec : new, but with an important difference. It pre-allocates space in the vector. Because we know we need to store size elements in the vector, doing this allocation up front is slightly more efficient than using vec : new, which resizes itself as elements are inserted. When you run cargo check again, you'll get a few more warnings, but it should succeed. A worker struct responsible for sending code from the thread pool to a thread. We left a comment in the for loop in listing 20-14 regarding the creation of threads. Here we'll look at how we actually create threads. The standard library provides thread : spawn as a way to create threads, and thread : spawn expects to get some code the thread should run as soon as the thread is created. However, in our case, we want to create the threads and have them wait for code that we'll send later. The standard library implementation of threads doesn't include any way to do that. We have to implement it manually. We'll implement this behavior by introducing a new data structure between the thread pool and the threads that will manage this new behavior. We'll call this data structure worker, which is a common term for pooling implementations. Think of people working in the kitchen at a restaurant. The workers wait until orders come in from customers, and then they're responsible for taking those orders and filling them. Instead of storing a vector with join handle less than parentheses greater than instance in the thread pool, we'll store instances of worker struct. Each worker will store a single join handle less than parentheses greater than instance. Then we'll implement a method on worker that will take a closure of code to run and send it to the already running thread for execution. We'll also give each worker an ID so we can distinguish between the different workers in the pool when logging or debugging. Let's make the following changes to what happens when we create a thread pool. We'll implement the code that sends the closure to the thread after we have workers set up this way. 1. Define a worker struct that holds an ID and join handle less than parentheses greater than. Change thread pool to hold a vector of worker instances. Define worker : new function that takes an ID number and returns a worker instance that holds an ID and a thread spawned with an empty closure. In thread pool : new, use the for loop counter to generate an ID. Create a new worker with that ID and store the worker in the vector. If you're up for the challenge, try implementing these changes on your own before looking at the code in listing 20-15. Ready? Here is listing 20-15 with one way to make the preceding modifications. Listing 20-15, modifying thread pool to hold worker instances instead of holding threads directly. We've changed the name of the field on thread pool from threads to workers because now holding worker instance and now it's holding worker instance instead of join handle less than parentheses greater than instance. We use the counter for the for loop as an argument to worker : new, and we store each new worker in the vector named workers. External code, like our server in source/bin/main.rs, doesn't need to know the implementation details regarding using a worker struct within thread pool. So we make the worker struct and its new function private. The worker : new function uses the ID we give it and stores the join handle less than parentheses greater than instance that is created by spawning a new thread using an empty closure. This code will compile and store the number of worker instances we specified as an argument to thread pool : new, but we're still not processing the closure that we get in execute. Let's look at how to do that next. Sending requests to threads via channels. Now we tackle the problem that the closure given to thread : spawn do absolutely nothing. Currently, we get the closure we want to execute in the execute method, but we need to give thread : spawn a closure to run when we create a worker during the creation of the thread pool. We want the worker struct that we just created to fetch code to run from a queue held in thread pool and send that code to its thread to run. In Chapter 16, you learned about channels, a simplest way to communicate between two threads that would be perfect for this use case. We'll use the channel to function as the queue of jobs and execute. We'll send a job from the thread pool to the worker instance, which will send the job to its thread. Here's the plan. 1. The thread pool will create a channel and hold on to the sending side of the channel. 2. Each worker will hold onto the receiving side of the channel. 3. We'll create a new job struct that will hold the closures we want to send down the channel. 4. The execute method will send the job we want to execute down the sending side of the channel. And 5. In its thread, the worker will loop over its receiving side of the channel and execute the closures of any jobs it receives. Let's start by creating a channel in thread pool : new and holding the sending side the thread pool instance as shown in listing 20-16. The job struct doesn't hold anything for now, but will be the type of item we're sending down the channel. Listing 20-16, modifying thread pool to store the sending end of channel that sends job instances. In thread pool : new, we create our new channel and have the pool holding the sending message. This will successfully compile still with warnings. Let's try passing a receiving end of the channel into each worker as the thread pool creates the channel. We know we want to use the receiving end in the thread that the workers spawn, so we'll reference the receiver parameter in the closure. The code in listing 20-17 won't quite compile yet. Listing 20-17, passing the receiver end of the channel to the workers. We've made some small and straightforward changes. We passed the receiving end of the channel into the worker : new, and then we used it inside the closure. When we try to check this code, we'll get an error. The code is trying to pass receiver to multiple worker instances. This won't work. As you'll recall from Chapter 16, the channel implementation that Rust provides is a multiple producer, single consumer. This means we can't just clone the consuming end of the channel to fix this code. Even if we could, that is not the technique we would use. Instead, we want to distribute the jobs across threads by sharing the single receiver among all the workers. Additionally, taking a job off the channel query involves mutating the receiver, so the threads need a safe way to share and modify receiver. Otherwise, we might get race conditions, as covered in Chapter 16. Recall the thread safe smart pointers discussed in Chapter 16 to share ownership across multiple threads and allow the threads to mutate the value. We need to use ARC less than mutex less than t greater than. The ARC type will let multiple workers own the receiver, and mutex will ensure that only one worker gets a job from the receiver at a time. Listing 20-18 shows the changes we need to make. Listing 20-18, sharing the receiving end of the channel among the workers using ARC and mutex. In thread pool : new, we put the receiving end of the channel in the ARC and mutex. For each new worker, we clone the ARC to bump the reference count so that the worker can share ownership of the receiving end. With these changes, the code compiles. We're getting there. Implementing the execute method. Let's finally implement the execute method on thread pool. We'll also change job from a struct to a type alias for a trait object that holds the type of closure that execute receives. As discussed in creating type synonyms with type aliases, section in Chapter 19, type aliases allow us to make long type shorter. Look at listing 20-19. Listing 20-19, creating a job type alias for a box that holds each closure, then sending the job down the channel. After creating a new job instance using the closure we get in execute, we send the job down the sending end of the channel. We're calling unwrap on send for the case that sending fails. This might happen if, for example, we stop all of our threads from executing, meaning the receiving end has stopped for receiving new messages. At the moment, we can't stop our threads from executing. Our threads continue executing as long as the pool exists. The reason we use unwrap is that we know the failure case won't happen, but the compiler doesn't know that. But we're not quite done yet. In the worker, our closure being passed to thread : spawn still only references the receiving end of the channel. Instead, we need the closure to loop forever, asking the receiver end of the channel for a job and running that job when it gets one. Let's make the change shown in listing 20-20 to worker : new. Listing 20-20, receiving and executing the jobs in the workers thread. Here we first call lock on the receiver to acquire mutex, and then we call unwrap to panic on any errors. Acquiring a lock might fail if the mutex is in the poison state, which can happen if some other thread panicked while holding the lock rather than releasing the lock. In this situation, calling unwrap to have the thread panic is the correct action to take. Feel free to change this unwrap to an expect with an error message that is meaningful to you. If we get the lock on mutex, we call receive to receive a job from the channel. A final unwrap moves past the errors here as well, which might occur if the thread holding the sending side of the channel has shut down, similar to how the send method returns error if the receiving side shuts down. The call to receive blocks, so if there is no job yet, the current thread will wait until the job becomes available. The mute x less than t greater than ensures that only the one worker thread at a time is trying to request a job. With the implementation of this trick, our thread pool is in a working state. Give it a cargo run and make some requests. Success. We now have a threaded pool that executes connections asynchronously. There are never more than 4 threads created, so our system won't get overloaded if the server receives a lot of requests. If we make a request to /sleep, the server will be able to serve other requests by having another thread run them. Note, if you open /sleep in multiple browser windows simultaneously, it might load once at a time in 5-second intervals. Some web browsers execute multiple instances of the same request simultaneously for caching reasons. This limitation is not caused by our web server. After learning about the while let loop in Chapter 18, you might be wondering why we didn't write the worker thread code as shown in listing 20-21. Listing 20-21, an alternative implementation of worker : new using while let. This code compiles and runs but doesn't result in the desired threading behavior. A slow request will still cause other requests to wait and be processed. The reason is somewhat subtle. The mutex struct has no public unlock method because the ownership of the lock is based on the lifetime of the mutex guard less than t greater than within the lock result less than mutex guard less than t greater than that the lock method returns at compile time. The borrow checker can then enforce the rule that a resource guarded by mutex cannot be accessed unless we hold the lock. But this implementation can also result in the lock being held longer than intended if we don't think carefully about the lifetime of mutex guard less than t greater than, because the values in the while expression remain in scope for the duration of the block. The lock remains held for the duration of the call to job parentheses, meaning other workers cannot receive jobs. By using loop instead of acquiring the lock and a job within the block rather than outside it, the mutex guard returned from the lock method is dropped as soon as the let job statement ends. This ensures that the lock is being held during the call to receive, but it is released before the call to job parentheses, allowing multiple requests to be serviced concurrently. Graceful shutdown and cleanup. The code in listing 20-21 is responding to requests asynchronously through the use of a thread pool. As we intended, we get some warnings about the worker's ID and thread fields that we're not using in a direct way that reminds us we're not cleaning up anything. When we use the less elegant Control-C method to halt the main thread, all the other threads stopped immediately as well, even if they're in the middle of serving a request. Now we'll implement a drop trait to call join on each of the threads in the pool so they can finish the requests they're working on before closing. Then we'll implement a way to tell the threads they should stop accepting new requests and shut down. To see this code in action, we'll modify our server to accept only 2 requests before gracefully shutting down its thread pool. Implementing the drop trait on thread pool. Let's start with implementing drop on our thread pool. When the pool is dropped, our threads should all join to make sure they're finished their work. Listing 20-23 shows a first attempt at a drop implementation. This code won't quite work yet. Listing 20-23, joining each thread when the thread pool goes out of scope. First, we loop through each of the thread pool workers. We use the reference mute for this because self is a mutable reference, and we also need to be able to mutate worker. For each worker, we print a message saying that this particular worker is shutting down, and then we call join on the other worker's thread. If the call to join fails, we use unwrap to make Russ panic and go into an ungraceful shutdown. Here is the error we get when we compile this code. The error tells us we can't call join because we have a mutable borrow of each worker, and join takes ownership of its argument. To solve this issue, we need to move the thread out of the worker instance that owns thread so join can consume the thread. We did this in listing 17-15. If worker holds an option less than thread join handle less than parentheses greater than, instead we can call the take method on the option to move the value out of some variant and leave the none variant in its place. In other words, a worker that is running will have a some variant in thread. And when we want to clean up a worker, we'll replace some with none so the worker doesn't have a thread to run. So we know we want to update the definition of worker like this. Now let's lean on the compiler to find other places that need to change. Checking this code will get 2 errors. Let's address the second error, which points to the code at the end of the worker : new. We need to wrap the thread value in some when we create a new new worker. Make the following changes to fix this error. The first error is in our drop implementation. We mentioned earlier that we intend to call take on the option value to move thread out of worker. The following changes will do so. As discussed in Chapter 17, the take method on option takes the some variant out and leaves none in its place. We're using if let to deconstructure the sum and get the thread. Then we call join on the thread. If a worker in thread is already none, we know that the worker has already had its thread cleaned up, so nothing happens in that case. Signaling to the threads to stop listening for jobs. With all of the changes we've made, our code compiles without any warnings. But the bad news is the code doesn't function the way we want it to yet. The key is the logic in the closures run by the threads of the worker instances. At the moment we call join, but that won't shut down the threads because they loop forever looking for jobs. If we try to drop our thread pool with our current implementation of drop, the main thread will block forever waiting for the first thread to finish. To fix this problem, we'll modify the threads so that they listen for either a job to run or a signal that they should stop listening and exit the infinite loop. Instead of job instances, our channel will send one of these two enumeration variants. This message enumeration will either be a new job variant that holds the job the thread should run, or it will be a terminate variant that will cause the thread to exit its loop and stop. We need to adjust the channel to use values of type message rather than type job as shown in listing 20-24. Listing 20-24, sending and receiving message values and exiting the loop if a worker receives message : terminate. To incorporate the message enumeration, we need to change job to message in 2 places: the definition of thread pool and the signature of worker : new. The execute method of thread pool needs to send jobs wrapped in the message : new job variant. Then in worker : new, where a message is received from the channel, the job will be processed if the new job variant is received, and the thread will break out of the loop and loop if the terminate variant is received. With these changes, the code will compile and continue to function in the same way as it did after listing 20-21, but we'll get a warning because we aren't creating any messages of the terminate variety. Let's fix the warning by changing our drop implementation to look like listing 20-25. Listing 20-25, sending message : terminate to the workers before calling join on each worker thread. We're now iterating over the workers twice, once to send the terminate message for each worker and once to call join on each worker's thread. If we tried to send a message and join immediately in the same loop, we couldn't guarantee that the worker in the current iteration would be the one to get the message from the channel. To better understand why we need two separate loops, imagine a scenario with two workers. If we use a single loop to iterate through each worker, on the first iteration, a terminate message would be sent down the channel and join call on the first worker's thread. If that first worker was busy processing a request at the moment, the second worker would pick up the terminate message from the channel and shut down. We wouldn't be left waiting on the first worker to shut down, but it never would because the second thread picked up the terminate message deadlock. To prevent this scenario, we first put all of our terminate messages on the channel in one loop. Then we join on all the threads in another loop. Each worker will stop receiving requests on the channel once it gets the terminate message. So we can be sure that if we send the same number of terminate messages as there are workers, each worker will receive a terminate message before join is called on its thread. To see this code in action, let's modify main to accept only two requests before gracefully shutting down the server, as shown in listing 20-26. Listing 20-26 shut down the server after serving two requests by exiting the loop. You wouldn't want a real-world web server to shut down after serving only two requests. This code just demonstrates what a graceful shutdown and cleanup is in working order. The take method is defined in the iterator trait and limits the iteration to the first two items at most. The thread pool will go out of scope at the end of main and the drop implementation will run. Start the server with cargo run and make 3 requests. The 3 requests should error, and in your terminal you should see output similar to this. You might see a different ordering of workers and messages printed. We can see how this code works from the messages. Worker 0 and 3 got the first 2 requests, and then on the third request the server stopped accepting connections. When the thread pool goes out of scope at the end of main, its dropped implementation kicks in and the pool tells all workers to terminate. The workers each print a message when they see the terminate message, and then the thread pool calls join to shut down each worker thread. Notice one interesting aspect of this particular execution. The thread pool sent the terminate messages down the channel, and before the worker received the messages, we tried to join worker 0. Worker 0 had not yet received the terminate message, so the main thread blocked waiting for worker 0 to finish. In the meantime, each of the workers received the terminate message. When the worker 0 finished, the main thread waited for the rest of the workers to finish. At that point, they had all received the termination message and were able to shut down. Congrats, we have now completed our project. We have a basic web server that uses a thread pool to respond asynchronously. We're able to perform a graceful shutdown of the server, which cleans up all the threads in the pool. Here is the full code for reference. We could do more here if you wanted to continue enhancing this project. Here are some ideas. Add more documentation to Threadpool and its public methods. Add tests of the library's functionality. Change calls to unwrap to more robust error handling. Use Threadpool to perform some tasks other than serving web requests. And find a Threadpool crate on crates.io and implement a similar web server using a crate instead. Then compare its API and robustness to the Threadpool we've implemented. Summary. Well done, you've made it to the end of the book. We want to thank you for joining us on this tour of Rust. You're now ready to implement on your own Rust projects and help with other people's projects. Keep in mind that there is a welcoming community of other Rusticians who would love to help you with any challenges you encounter on your Rust journey. Well, that completes the book and the final chapter, chapter 20. And yeah, it was long, and I guess this is the end.